Hello everybody, good morning and good evening. Thank you for joining us today. You are part of the 358 people worldwide who have registered to view this webcast powered by Yole Développement, KnowMade, System Plus, and sponsored by AT&S, dedicated to advanced substrates. My name is Faisal El-Kamasi. I'm Global Sales Support and Coordinator for Yole Développement. Before we get started with this webcast, I would like to give you some information regarding the logistics. You have the possibility during all the webcast to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining question, we will make a following up via emails within a week. Concerning the material and contents, please note that the presentation is available and downloadable in the resources section. You will also receive an email after the webcast within 24 hours with a link to the recorded session. So today, Yole Développement, KnowMade, AT&S, and System Plus Consulting will share their analysis for you on advanced substrates. First, let's start with a presentation of advanced substrates presented by Vivienne Chu, Technology and Market Analyst at Yole Développement. She is specialized in the advanced packaging and semiconductor manufacturing sectors. Vivienne, please.
So thank you, Faisal. Welcome again to our webcast, everybody. Today, I would like to present how advanced substrate can answer the demands of both the scaling and functional roadmaps. So today, I would like to start first by briefly introducing Yole Développement. Then we'll talk about the market and the technology trends that we see. Later on, for the scaling roadmap, we would like to introduce the appearance of SLP, so substrate-like PCBs from last year. And from the functional roadmap, we'll talk about the embedded die technology. At last, of course, we'll have a brief summary about my presentation. So, first of all, Yole is a semiconductor technology and market strategy consulting company. We have different fields of activities to cover diverse subjects. So in my team, we cover mostly advanced packaging, which we look at how chips are packaged. This is the back end of the process. And then me, myself, I am more in the activity of advanced substrate, which we look at both substrates and PCB activities. So before we start the market and technology trends, I would like to give you our definition about substrate and PCB. So IC substrate serves as an interconnection between the chip and the PCB. So basically, the chip will be integrated on top of the substrate and then attached to a PCB. A PCB is the final board. So basically, it would be the green board if you break down your laptop. That is exactly what we're talking about as PCB. So now for the market and technology trends. So on this page, you can see the graph. The blue curve represents the feature size of a chip. The green curve represents the feature size of a PCB. As we can see, the feature size of a chip decreased way faster than PCB during the past decades. So in 1970, the gap wasn't so significant, but nowadays, the gap became so large. This gap actually makes packaging challenging, but it also creates opportunities. On the other hand, it also pushes the board to innovate. Well, of course, during the path of innovation, we have certain different drivers. So if we talk about dimensional-wise, we would like to decrease the line in space because we would want to integrate more chips on the specific surface. And we would like to decrease the thickness because we ask for smaller devices nowadays. On the other hand, for the technical part, we would like better electrical performance and better thermal management. All of these, of course, we would not want to have a device or an end product that is too expensive that nobody can afford. So all of these would be also controlled by cost. We would like to have lower cost. Now the technology. So On this graph, on the y-axis, we can see the layer thickness, which is the copper plus the dielectric. And on the x-axis, we'll see the line and space size. So here we see some standard technologies for normally a dedicated featured size. So for the smallest featured size, we see copper damascene, which is normally used for wafer processing. This is the front end of the process. For the largest featured size, which is around 30 to 30 microns, we see the technology of subtractive. This is a traditional technology that is used for the board, so the PCB. In the middle, we see a semi-additive process for thin film RDL or substrates. These are actually technologies for packaging. So as packaging actually has a featured size that overlaps a little bit with both the CU damascene technology and the subtractive technology, this can create certain zones of competition. So in this page, we see the 3 competition zones that we identified. So the first one is between the board and the IC substrate. The second one would be the substrate and the wafer level packaging, when wafer level packaging actually don't require a substrate. And on the third part, we see a high density fan out and 2.5D IC. So all of these technologies, so in each competition zones, there are 2 technologies that can achieve the same demand of featured size. But there is no certainty of which technology is better than the other one, which is why these are areas of competition. In the webcast today, we are more focused on the 2 areas that is marked on this page. So the first one is between the board and the IC. This is what we see as the new product of substrate-like-PCB. And the second one would be the embedded die in substrate. So let's talk about the substrate-like-PCB for the scaling roadmap. So this was demanded by Apple in 2017 in their latest iPhone. And I would like to start with 2 fast definitions. So SLP is the board that was used in the latest iPhones, in the cell phone, so it's the product. MSAP, which stands for Modified Semi-Additive Process, is the technology that is normally used for IC substrates, but also, so that is the technology. So why does Apple demand this? So the main idea is to decrease the line and space, as we mentioned previously, and to gain control of the process. As we can see, well, we found out that in iPhone 8 and iPhone 10, the SLP is actually manufactured by a mix of both subtractive and MSAP process. You'll probably hear more from System Plus later on. In the table, some of the players we have identified for having the capacity of fabricating with MSAP technology. And we also identified several Apple's SLP supplier, including AT&S, who you will hear from later on. So what exactly is the influence of SLP? First of all, it creates a competition between PCB and substrate manufacturers. Basically, PCB manufacturer, if they have a technology transition, they'll be able to enter the zone. And for the IC substrate manufacturers, since they already hold the technology of MSAP, it's a possibility that they start to have activities in the zone as well. Currently, we see some flagship smartphones adapted SLP, and we're still looking if there are other products that would also adapt SLP. Here, I would like to show you a glance of the SLP market forecast that we have. So for the units, we see a growth rate of 59.4% in the next 5 years. And for the revenue of SLP, we also see a growth of 51% in the next 5 years. We estimate there are other cell phone players, apart from the several ones right now, that will follow the adoption of SLP in their later cell phones. So we see promising growth of SLP adoption in the near future. Now, let's look at the functional roadmap, which is the embedded die technology. So embedded die, as what it describes, it's when you put a die in a substrate instead of on top of it. There are several different reasons that different applications or different players are interested in this kind of technology. First of all, it's the form factor, because we decrease the thickness. Secondly, it's for better thermal management or to protect the die from harsh external environment. The third, we have shorter interconnections or higher component integrations. So each of them has their own choice. Here at Yole, we have 4 different kind of segmentations for the embedded die technology. So if we embed active or passive dies, basically we can embed die in the laminate, so the substrate, or embed it in the PCB, which is the board, or we can embed it in flexible substrate or PCB. On the other hand, we can also embed passive interconnections. This is basically the technology of Intel, which they embed their interconnection in the substrate in order to connect the dies on top of it. So in these different 4 segmentations, we see different players present in each category and with their own proper technology. You will probably hear the IC landscape of these 4 technologies from Nicolas later on. Well, since we said that embedded die is fairly new, but actually embedded die packages are already present in products at different stages. For example, in the R&D level, we would like to have automotive power switch. Sometimes they are more blocked in the qualification level because in some industry it takes longer time for these. And also we see already commercialized products such as a lower power DC-DC converter and so on. And actually, we also see this technology or this kind of package in different kinds of applications, such as the Bluetooth module in the cell phone, hearing aid for the medical applications, wearables, military, data center, and even automotive. So this is actually what we see at the moment. At last, I would like to sum up my presentation quickly. So the first thing I would like to convey to you is that there are gaps that need to be filled, as we showed at the very beginning. So this actually creates opportunity and challenges for packaging, and it also creates opportunity for different business models. Secondly, there's a technology transition from subtractive process to MSAP for cell phone boards. Thirdly, we see promising growth of the SLP market, which reaches 440 million units and $2.2 billion in 2023. For embedded die, there are different reasons for adapting for embedded die, depending on the applications and depending on their demand. And most of these players, they develop their own proper technology, and they decide who to license it to and who to manufacture it with for these embedded die packages. So this is the end of my presentation. Most of my slides are extracted from our latest report, Status of Advanced Substrates. I hope you enjoy my presentation, and please do not hesitate to ask questions in the Q&A window. Thank you very much.
Thank you very much, Viviane, for this very interesting presentation. Yes, as Viviane said, once again, do not hesitate to ask questions using the Q&A button for the Q&A session at the end of the webcast. So we will continue with a technology review from Stéphane Elisabeth, RF Sensor and Advanced Packaging Costing Engineer at System Plus Consulting. Stéphane, please.
Hi, everyone. I'm Stéphane Elisabeth, Cost Engineer at System Plus Consulting. I'm in charge of RF in image sensor and advanced packaging, and I will present some technologies using advanced substrates. So to begin with, I will present the company. Here at System Plus, we provide reports on several devices in many application domains. In the case of advanced substrates, we have currently almost 10 reports of subjects like microchip from Texas Instruments. Advanced substrates allows thin design and very small form factor components that could be integrated in devices with high space constraints. Today, board and substrates are sharing the same goal, providing small form factor solution with higher performance at lower cost. And to provide such solution, 2 main technologies is on the market now, trying to fulfill the need. So first of all, there is the substrate-like-PCB technology, where a mix of IC substrate manufacturing technology and subtractive process leads to advanced substrate with line space below 30 microns. And in the market, we could find several actors manufacturing SLP, but only 2 smartphone OEMs managed to integrate such technologies inside their high-end products. In partnership with several companies, the 2 OEMs have shown to the world the feasibility and the reliability of the SLP manufacturing. But both with different goals. In the iPhone X, Apple chose to use 2 pieces of SLP and a via frame, making the connection between the 2 boards, leading to a footprint board at 1.5K millimeter square, whereas Samsung has only 1 SLP, 2 times larger than the iPhone X board. But to understand the different choice, we can take a look at the comparison with the previous generation of each smartphone. For Apple, for example, the iPhone X and the iPhone 8 were released with a gap of 2 months. But Apple want to plan a huge milestone in the smartphone world for the iPhone 10th anniversary. And to do that, they managed to improve a large amount of components inside the iPhone 8 to provide a more high-end smartphone. So reusing almost 17% of the iPhone 8 components and integrating SLP technology, they managed to increase the PCB area, but by about 40% in a space and in an actual space, smaller by 14%. Which allows Apple to integrate more rear-facing function, for example, and also larger battery. In the other side, in its regular flagship, the Galaxy S9, Samsung introduced a small innovation like dual camera, integrated mid and high band LTE phone modules, or new heart sensor. And all result in an increase of the bill of materials and the release of only 3 worldwide versions compared to the 10 available versions of the S8. The use of SLP gives higher performance, but doesn't provide smaller PCB in this case. In fact, Samsung chose to increase by 16% the PCB area. And finally, in the A11 report, we provide some measurement of the PCB line space for the Apple, revealing that the SLP suppliers, including AT&S, managed to provide quite low roots dimension. And currently, we are under the analysis of the Galaxy S9 Plus and its Exynos 9. But first, basic analysis reveal low dimension under 30 microns. In the second part, we can say that embedded die is the technology allowing very small form factor and from some application enhance thermal management. And over the years, since 2012, 2 main players have been identified on the market, among several others. For example, AT&S supplying big companies like Texas Instruments or GAD Systems, mainly to provide solutions in power devices. And for this technology, the power die is embedded in a middle prepreg. And for the GaN device, several copper connections linked to the substrate to the top copper metal layer, providing thermal dissipation. And the second player identified is TDK, targeting also power application, but recently spread its target to wireless and audio devices. And the possibility to embed the main IC could lead to high size reduction and can be very interesting to IoT and wearable devices. So integrated Bluetooth IC along with the balloon and the external component in the device with 12 millimeters square could be done as shown by TDK. And compared to a separated solution, it allows a decrease by almost 80% of the footprint. And so with such a small form factor in automotive and the embedded die is already a hard competitive application, which lead the manufacturer to look around and going to another like IoT, where they can have a high value. So in terms of cost, we as TCentrals show that the TDK solution is higher than the ATNS solution, but it's also for different purposes, where TDK use resin materials to embed the IC die, ATNS use prepreg to embed the power die, which lead to higher embedded process costs for the system technology. So finally, to conclude, I would say that SLC devices will grow in the next few years, starting now. As it's already integrated in high-end consumer devices, the technology is mature enough to spread in this application area and other like wearable. And in this same application, where embedded die has also a key to play with very high small form factor and enhanced thermal management. And thank you.
Thank you very much, Stéphane, for your interesting presentation. Okay, so let's carry on. Nicolas Baron, CEO and co-founder of KnowMade, will now provide a patent landscape of the advanced substrates. Please, Nicolas.
Okay, thank you, Faisal, for the introduction. At KnowMade, we daily track patents related to advanced packaging, and also we analyze the patent landscape. And today, in my presentation, I will show you some results from our analysis of patents related to dies and also interconnects embedded in substrates. I would like to start with the time evolution of patent publication. As of today, more than 7,100 patents have been published worldwide in gray color on the graph. And these patents are grouped in more than 3,100 patent families in blue, the bar graph in blue color on the graph. Just a brief definition for patent family. A patent family is a set of patents filed in multiple countries to protect one single invention. As you can see, the level of patent activity took off from 2000 and then accelerated significantly from 2004. But since 2007, we have observed a continuous decrease of the patenting activity, while a second wave of patent extensions worldwide was occurring. So this kind of IP dynamic is typically reflects a mature technology. So according to the time evolution of patent publications, and especially with the acceleration of the decrease of patent publications the past few years, we can assume that the great majority of technical solutions for solving embedded die-related problems seems to be already in the patent. Okay, on the next page, this bar graph shows the main patent assignees according the number of their patent families. The top 10 companies hold more than 50% of patent filings. And Samsung Electromechanics has the most important patenting activities with more than 300 families, followed by Unimicron, Kyocera, Murata, and Panasonic. In this graph, we can note that only few research organizations are present in the embedded die IP landscape. And the largest one is the Industrial Technology Research Institute of Taiwan, with 22 families. The few number of research organizations in the IP landscape is a sign of the technology maturity of the embedded die packaging, as deduced from the IP dynamics shown in the previous page. Okay, now regarding the legal status of the patents, on the left, the donut chart, almost 50% of the patents are currently in force, in green color on the chart. And the patent application currently pending in blue represents only a small part of the patent. So we have 3 more times granted patents than pending patent applications. Through this donut chart confirms the maturity of the embedded die technologies. The bar graph shows the same ranking of IP players previously seen, but with the current legal status of their patents. The granted patents in green color, the pending patent application in blue, and the dead patents in red. As you can see, there are some discrepancies between the patenting activity of an organization and the real number of its patents currently in force. For example, Samsung Electromechanics shows the most important patenting activities with the higher number of patent filings related to embedded die technology, but only 1/3 of its patents are currently granted. Now, regarding the number of granted patents, the pie chart on the right shows that Samsung Electromechanics is leading the embedded die IP landscape with 9% of enforceable patents, followed by Intel and Ebiden, that each holds 7% of granted patents. And then we have Murata with 6%, Shinko and Unimicron with 5%. In terms of patent filings, Intel and Samsung Electromechanics are currently the major patent applicants, which for each of them 12% of patent application currently pending, followed by Murata and Ebiden with 6%. On the bar graph, now if we consider Qualcomm, AT&S, and Meiko Electronics, we can see the important share of their pending patent applications, which represents more than 50% of their live patents. So Qualcomm, AT&S, and Meiko Electronics are younger in the IP landscape, and they can be considered as new IP changers in the field. On the contrary, some companies are less active in terms of patent filings, with only few patent applications currently pending, like, for example, Unimicron, Shinko, Kyocera, Panasonic, or NGK Sparkplug. Okay, these differences of past and current patenting activity between the key players involved in embedded die technologies are well visible on this graph that shows the time evolution of patent publication for each patent assignee. We can easily identify the old patent applicants now inactive in terms of patent filings. Those which were less active the past 5 years, like Unimicron, Chinko, Kyocera, Panasonic, or NGK. Also, we can see the companies that recently increased their patenting activity in the field, like Samsung Electromechanics. And also we can identify the new entrants in the patent landscape, like Qualcomm and Mako Electronics. Okay, now regarding the different packaging platforms for embedded dies, we know the companies involved in each platform. We know them from the market perspective. For example, for dies packaged between layers of laminates, we know TDK, HNS, or Chinko. For dies packaged between layers of flexible laminates, we know Fujikura and its WABE technology. And of course, for interconnections embedded in substrate, we know Intel and its EMIB technology. Okay, we know these players from a market perspective, but from a patent perspective, who has the patents? Who are the main IP players? So in our patent investigation, we have identified the main IP players for each packaging platforms. And as you can see, there are discrepancies between the well-known market players and the players which have the patents. I mean, the players which have a key IP position. For example, for dies embedded in laminate, TDK or HNS have weaker IP positions than Ibiden, NGK Sparkplug, or Samsung Electromechanics. For flexible substrates, beside Fujikura, we have identified a lot of companies having patents related to dies packaged between layers of flexible substrates, flexible laminates, sorry, like Ibiden, Samsung Electromechanics, Murata, or ITNS. And finally, concerning the silicon bridge embedded in substrates, we, of course, identified the patents of Intel, but also we have identified numerous other patents from other different organizations, like Qualcomm. And at last, to finish my presentation, I would like to show you one example of an US patent recently granted to Qualcomm, and which claims a semiconductor package with identity die-to-die connections. This patent relates to a bridge structure embedded in the substrate, and this bridge structure is configured to provide an electrical connection between the first die and the second die. And the first and second dies are configured to be coupled to the substrates. And also, according to these patents, the bridge may be silicon or organic, and the bridge may have sub-micron design capability. Okay, thank you for your attention.
Thank you, Nicolas. Thank you very much for this interesting presentation on the patent landscape. This is now Steve Anderson's turn to present his analysis of the advanced substrates. He is Director Strategy and Business Development at AT&S. Steve, the floor is yours.
Thanks very much. Hi, everyone. We're pleased to be able to share our thoughts and directions on advanced substrates following what Yole has introduced. Our agenda will be broken down in 4 key areas. First, an overview of the AT&S, followed by new substrate-like-PCB technology we just discussed. Then our work on developing advanced substrates and PCBs, ending with a summary. AT&S is a PCB and substrate supplier with a long history of serving multiple market segments, including computer, consumer, communications, and industrial. where we rank number 3 worldwide as a provider of high-end technology, with 6 plants in Europe and Asia, supporting major customers and focused on innovation solutions for our customers. Our major markets are broken into 5 key industry segments. These support growth products such as smartphones, computers, servers, automotive, IoT, and medical applications. All of these interesting areas for advanced substrates, as we just heard. We focus on providing our customers advanced PCB and substrate solutions, as well as their capacity requirement needs. If we now look at the advanced high-end interconnect, we're broken down into really 3 key areas that we look at. The embedding technologies you heard about, IC substrates used to connect ICs to PCBs, which are also getting very advanced into 3D configurations, and then our newest substrate-like-PCB technology on the right. The substrate-like PCBs utilize the MSAP additive plating as well as other manufacturing improvements to combine the best of HDI PCB technology with substrate technology. And what we see emerging is really a new miniaturization where the PCBs shrink to become system-level modules. If we now look at the what MSAP can do combining PCB and substrate technology, we see a lot we've heard about the focus today with more than Moore's Law, where interconnect reduction plays an increasingly critical role to achieve system performance. We are working to combine the best of the HDI plus substrate technology for what's called, as we heard, the substrate-like PCB technology. This technology is used for some of the latest high-end smartphones and enables a new level of miniaturization, improving line space reduction capabilities, electrical performance, line shape control, and routing capabilities. If we look at these advantages further, we first see that the substrate-like PCBs, in this first example, improve signal integrity. They provide better roughness, shape control, and tolerancing due to the improved additive plating, plus the use of new high-speed, high-frequency materials. If we then look at the next advantage, we can see a thickness reduction as thinner laminate and metal layers are possible, as well as thinner cores or coreless structures evolve. And then finally, the third aspect is that signal routing density can be improved with more traces between pad bumps and finer line spaces. All of these are required now by these emerging 5G, IoT, high-performance computing, and other emerging applications, as well as a new level of integration that Yole just discussed. We discussed embedding, which we're a key player, and increasingly what we see is more passives and actives being embedded into the PCB or substrate structure to reduce Z height, as seen in this chart. Not only Z height reductions are possible, but also power level reductions. Power level reductions sorry here. Yeah, power level reductions. If we look then at miniaturization, what's happening is over the years, the trends of smartphones and other mobile devices to shrink the size of electronics in order to get better battery, screen size, and more sensors or artificial intelligence functions integrated. The advent of the new MSAP plating and this capability for substrate-like PCBs brings the best of both capabilities to the industry. We think that we'll expect to see much smaller, more modular component integration over the next 5 years, approaching an all-in-one type of module. The other, one of the biggest interconnect landscape changes we are seeing is the advent of smart modules creating miniaturized smart systems where the PCB or main board really becomes the system. The evolution of multi-chip packages to system and package is seeing now another major evolution with these system-like PCB technologies to enable new smarter systems. The smart systems in our definition combine key functions of power management, computing, memory storage, as well as connectivity to create a smart system module or what we call fan-out system in board. This module integration has a couple of key advantages that are important, we think. One is time to market. Advantages are improved as you reduce the number of packaging steps you might need depending on your design and what you may do with embedding. Time to market's also improved as components are integrated. System costs can be optimized and reduced. Form factors can be reduced or customized to applications more effectively. The overall performance, we believe, is improved due to the total reduction of interconnect delays and matching the best materials for the application. Another example here of what we're looking at in the fan-out system and board, again, using these PCB and substrate technologies, what we discussed as substrate-like-PCB, where we combine embedding a couple of chips with components on top and bottom. Recently, the development of the fan-out packaging with products such as Info from TSMC, RCP from NXP, or EWB from Infineon have gained prominence to help bring new technologies that, again, can be combined with substrate-like PCBs to make a much smaller system. So we're combining these fan-out concepts with various 2.5D concepts to create what we call fan-out system and boards. As an example, you can see the embedding of multiple components in this slide, where in the substrate, which when combined with components on top and bottom can create a much smaller system with shorter interconnects and higher performance. While this technology is in the development stage now, it's expected to ramp up and play a key role in future 5G and mobile products in the next 5 years. A key feature of these smart systems supported by this integration is the ability to get better power management, especially with multiple fab lithography voltage levels that we're seeing increasingly in the future. This example we're showing on the left is an embedded power device with passives on top and bottom, which enables a smarter power management function, while on the right, we're showing the integration of heat pipes. Again, when you combine PCBs with substrates, it's possible to get new kinds of capabilities, bring the best of the substrate and the best of the PCB together into these new module configurations. Then another big area in the market right now is 5G and new technologies emerging. So another significant requirement in creating these smart systems is the ability to cost-effectively manage high-frequency signals with high-speed signals, optimizing both the materials and manufacturing methods. In this example, we show that 5G and other new autonomous auto radar technologies require higher frequencies and lower loss materials. If we could integrate these higher performance materials into standard PCBs and substrates as shown in the center, we achieve lower cost systems because we can optimize the use of materials in each case. We also can add filters and antenna structures as shown on the right. These future smart systems require a new level of co-design, but also more opportunity to combine different elements and types of PCB technology to achieve the design goals. In summary, What we see is a new world of design opportunity created by these substrate-like PCBs, where we can manage increasing signal integrity challenges as well as creating a new level of miniaturization, leading to smarter systems. We showed some of our technology and developments here, such as embedding the fan-out concepts mixed with substrate-like PCBs. And we feel that these can truly help create more miniaturized systems and interconnect options for our customers in the future. Thank you for your time and attention.
Thank you very much, Steve. Thank you, all of you, for those relevant presentations. So we are now going to wrap up with a Q&A session. We will answer as many questions today as time permits, and follow up via emails on the remaining questions. So we have a lot of questions, so there is a lot of interest from the attendees. So Vivienne, maybe one question for you. What are the main difficulties for embedded die technology?
Wow. So for difficulties for embedded die technologies, we can, let's say, separate them into 3 big points. The first one would be that since this is a technology that has not been standardized yet in the industry, each player has their own technology and own process, the supply chain for the embedded die is not mature yet. So for example, most of the substrate makers have just joined the packaging field, and this technology has raised a shared responsibility between, well, the packaging, so the OSATs and the substrate makers, and also the IDMs. So for example, if today, when a die is finally embedded in substrates, and then later on we found out that this package has failed, who is responsible for the failure? Is it the die that failed, or is it the process of embedding it actually made it failed? This evokes one of the questions. On the second point, after embedding the die in the substrate or in the PCB in the flex, it became hard to test the final product. So we'll have less nodes to test the die, and it'll also give a difficulty to repair such a product at the end. And the third point is that until now, sometimes the cost of the embedded die package is still too high, and that in certain cases, the yield is still too low for such a cost. So this is what we see for the difficulties of embedded die technology today.
Okay, thank you, Vivienne. That's quite clear. Stefan, one question for you. Besides SLP, do you see any further advanced substrate applications coming this year?
Okay.
Yes, I think yes, we do see further ones coming. We think that what SOP is doing is starting the advent of new technologies. And what is likely to see is more embedding of other functions like antennas and other capabilities as people look at design rules and understand the manufacturing capabilities.
Okay, thank you, Steve. Yeah, one of the questions, Steve, would be, you mentioned that advanced substrates enable more miniaturization. How do you differentiate smart system modules versus SiP or system in package?
Yeah, so for this definition, we're defining smart systems as containing the key power, computing, memory, and connectivity functions, which make a basic smart system, versus what system and package typically only includes some of those functions. So it's really an effort to define what a smart system could look like versus a module or a part of a smart system. So that's the difference.
Okay, now a question for Stephen. Okay, Stephen, why embedded die isn't it still applied to mobile APE?
Okay. Yeah, it's a hard question, I think. I think mostly because I think mostly because it will require I think more co-design between the companies, the manufacturing of the PCB and the foundry to provide a nice environment to fulfill the processor requirement. I think also there is the thermal management that could be maybe another issue, because most likely today we saw that the memory die is on top of the processor, and it's also a device that requires a thermal dissipation. So it could be applied, but maybe it also the cost is not very so efficient compared to POP technology that we have seen today.
Okay, thank you very much, Stéphane. So we are running out of time, so we have many questions, but the time is gone, so we'll follow up via emails on the remaining question. So, okay, the webcast is ending. Within the next 24 hours, you will receive an email that will include the recorded session. Please feel free to share the presentation with who will benefit from the information that has been presented, and find all our analyses and reports on our micronews.com website. Thank you for joining us today. Do not hesitate to contact us if you have additional questions. You can find your appropriate contacts on the last slides of the presentation. Have a good day. Bye-bye.